Once we've selected a trial asphalt content, our next step is to actually fabricate an asphalt mixture specimen and then perform measurements of its volumetric properties to determine whether or not the design aggregate gradation will pass or whether we need to move to a different aggregate gradation. We'll walk through an example just as we have for the past videos, and we'll use a trial asphalt content of 5.7%, which we calculated in the previous video. I've also recapped some other design information which we'll need, which is also provided in the introductory video. Prior to fabricating asphalt mixture specimens, we have to select a mixing and a compaction temperature. We do this on the basis of asphalt binder viscosity. To determine our mixing and compaction temperatures, we measure our binder viscosity using the rotational viscometer at 2 temperatures. Hence, you see 2 data points here. We then interpolate between the viscosity values at those 2 temperatures to see where we meet the target viscosity ranges for compaction and mixing. The gray bars show the target viscosity ranges. We can see that we selected our mixing temperature to be 155 degrees Celsius, and if we look at the graph here, we see that at 155 degrees Celsius, our viscosity falls within the target range. Similarly, we can see that we selected our compaction temperature to be 140 degrees Celsius. Again, if we look at the viscosity temperature relationship, we see that we fall within the target viscosity range for compaction at 140 degrees Celsius. You notice that we use lower viscosity and hence higher temperature for mixing than compaction. This is because we require a lower binder viscosity to coat our aggregate particles during the mixing process than we require during the compaction process. We will briefly review asphalt mixture sample preparation in this video. Additional details can be found in the laboratory demonstration videos. Our first step is to batch our aggregates. In the batching process, we place pre-weighed aggregates in the desired proportions into pans to ease our sample preparation process. Our asphalt binder, aggregate, and all of our mixing tools that will be placed in contact with the asphalt and aggregate during the mixing process are placed in an oven at the mixing temperature. Once all ingredients have reached the mixing temperature, they're removed from the oven and the asphalt and aggregate are combined in the desired proportions and mixed in a bucket mixer. After mixing, we place our loose asphalt mixture in an oven for 2 hours at the compaction temperature to simulate short-term aging. This allows for simulation of the oxidation that will occur during asphalt concrete production and placement, and also allow for the binder to fully absorb into the aggregate particles. After short-term aging, we take some of the loose mixture and use it to determine the theoretical maximum specific gravity. This is the specific gravity of the mixture if it contained no air voids. We compact our asphalt mixtures using the SuperPave gyratory compactor. A schematic of the SuperPave gyratory compactor is shown on this slide. It contains a reaction frame and a loading ram, which apply pressure to the loose asphalt mixture, which we place in a mold. The mold rotates on a base where it tilts back and forth at an angle of 1.25 degrees to simulate both the pressure and shearing action that we get from tires. In addition, we have a control and data acquisition panel that records the height of the specimen throughout the compaction process. As the mix densifies, the height will reduce, and a plot will form that looks like the one shown on this slide. We specify the compaction level based on the number of gyrations, or rotations, that the mold takes within the SuperPave gyratory compactor. We apply different numbers of gyrations within the SuperPave gyratory compactor to simulate the densification that asphalt mixtures would undergo under different traffic scenarios. We always consider 3 critical gyration counts: an initial, end design, and end max. An initial is used as a measure of mixture compactability during the construction process. End design is used to simulate the compaction under construction plus traffic throughout the pavement service life. And max is a very severe compaction effort that would never be exceeded in the field. For our example, we're in the range of 3 to 30 million ESELs. Therefore, our N initial will be 8 gyrations, our N design will be 100 gyrations, and our N max will be 160 gyrations. Now that we've covered the specimen fabrication procedure, we will go over some sample results. For our example, we will assume that we had a sample mass which was fixed at 4,700 grams. We'll assume that we measured our theoretical maximum specific gravity to be 2.408 and that we measured our asphalt mixture bulk specific gravity after Nmax gyrations to be 2.354. We also have height records throughout the compaction process. At N initial, we see our height was 129 millimeters. At 100 gyrations, we see that our height was 117.8. And at our final compaction level, N max, we see that our height was 116 millimeters. We measured the bulk specific gravity of our asphalt mixture specimen after the compaction process is completed. This corresponds to the N max gyration count. We cover how you do this procedure in the asphalt lab demo videos, and therefore we won't cover it here. However, equation 8 shows you how the bulk specific gravity is calculated. For our example, we'll assume that our bulk specific gravity at N max was measured to be 2.354. In addition to measuring our bulk specific gravity after the compaction process is complete, we can estimate our bulk specific gravity evolution throughout the compaction process using our height records. When we do this, we use equations 11 and 12. By viewing equation 12, it can be seen that when we do this estimation, we assume that the asphalt mixture specimen has a perfect cylindrical geometry. This leads to some error because there's aggregates which lead to an irregular surface on our specimens. We will estimate the bulk specific gravity at N max and then compare to the actual measured value. First, we need to calculate our estimated volume. We'll do this at N max again. So here we have pi times our diameter, which is fixed at 150. And we multiply that by our height, which at N max is 116. We divide by 4 and then multiply by a unit conversion factor, which gives us a volume of 2049.89 cubic centimeters. Now that we've estimated our volume at N max, we can calculate our estimated bulk specific gravity. Our sample mass is 4,700. We divide that by our estimated volume, 2,049.89, and we divide this quantity by the density of water, which is 1 gram per centimeter cubed. This gives us an estimated bulk specific gravity of 2.293. Recall that our measured bulk specific gravity was 2.354. Therefore, there is some error in our estimated value. Using the difference between our estimated and measured bulk specific gravities at N max, we will calculate a correction factor C using equation 10 that can be applied to correct our other estimates of specific gravity at N initial and N design, where we were not able to measure our actual specific gravity. For our example, C is calculated as the ratio between our measured bulk specific gravity, which was 2.354, over our estimated, which was 2.293, which gives us a correction factor value of 1.027. We use the calculated correction factor to correct our estimates of our bulk specific gravity at N initial and N max. The corrected values are tabulated in this table using equation 13. You'll notice that the corrected bulk specific gravities are slightly higher than the estimated. Recall that our correction factor was 1.027, which is going to raise the estimated by a slight amount, and so the numbers make sense. After we correct our estimates of bulk specific gravity, we combine those values with our measured theoretical maximum specific gravity, GMM, to calculate our percentage of our theoretical maximum specific gravity using equation 14. The tabulated values in the table show these calculations for gyrations of 8, 100, and 160. We then generate a compaction curve of our percent GMM versus gyration. As our mix densifies, as the gyration count increases, we come closer to our GMM value, and thus you see an increasing trend.